In this lesson, we will be discussing the movement of a force about an axis. Shown here on the left is a three-dimensional problem where we have a certain force F applied at one end of a bracket. If force F is equal to 450 newtons, determine the magnitude of the moment produced by this force about the x-axis. We first recall the formula to compute the moment about an axis is given by mx. X stands for the axis about which we are taking the moment, equal to ux cap, which is the unit vector pointing in the positive x direction, dot r cross f. Here r is a vector that extends from any point on the x-axis, which we are taking the moments, to any point which lies on the line of action of the applied force shown by this red color dashed line here. So for simplicity, we will choose the vector pointing from point A to point B as our r vector. So our r vector points from A to B. This is our r, A, B. So the first step is to compute the r vector, RAB is equal to, now look carefully at this vector RAB. It is moving in the negative x direction by 0.15 meters. So I write minus 0.15 I. It is also moving in the y direction by 0.3 meters. So plus 0.3 J. And finally, it is also moving upwards in the positive z direction by 0.1 meters. So plus 0.1 K. And of course, the unit is in meters. The next step is to compute the force vector also in vector notation. So force F is given by its magnitude multiplied by the unit vector in the direction of F. Now this unit vector, we can use the direction cosine since all the angles are given. So for the direction cosine, the x-axis is actually cosine 120 degrees I. Why is it 120 degrees? Now look carefully that the force F makes an angle of 60 degrees with the negative x-axis. This is the negative x-axis. So it is actually making an angle of 120 degrees with the positive x-axis. So the positive x is here, pointing in this direction. So the angle that F makes with the positive x-axis is actually here. And this is 120 degrees. And then the next direction cosine is in the y direction. The force F is making an angle of 60 degrees with the positive y-axis. So we just plus cosine 60 degrees J. And finally, the force F is making an angle of 45 degrees with the positive z direction. So plus cosine 45 degrees K. Alright, and we also know that the magnitude of force F is 450 newtons as given in the question. So here we can compute it one by one or use a calculator vector function to compute the answer. So in your calculator, go to menu and move on to the vector function. Here we define a certain vector A with dimension as 3, and the first element is cosine 120, so cos 120 equal. The second element is cosine 60 equal. Third element is cosine 45. So it is supposed to be multiplied with the scalar f, which is 450. So we go back to option, and then we say vector cal. We choose the vector just defined, which is vector A, multiplied by 450. And that will give us the answer as minus 225 I plus 225 J and then plus 318.20 K. So minus 225i plus 225j plus 318.20k, and this is in newtons. So finally, using this formula here, we can compute the moment about the positive x direction, and x is equal to the unit vector in the positive x direction is simply I dot RAB cross F. And in determinant notation, this is equal to 1, 0, 0, minus 0.15, 0.3, 0.1, minus 225, 225, 318.2. Now this once again can be computed using a calculator. In a calculator, go to manual and move on to matrix, option 4, and then we define matrix A. Number of rows is 3, number of columns is 3. First element is just 1. This element is 0. Then we move down minus 0.15, 0.3, 0.1, minus 225, 318.2. Notice that I made a mistake here when I enter minus 0.5. It is supposed to be minus 0.15, but this will not have an impact on the final answer because of the 2 zeros in the top row, as I will show you in a moment. Okay, then we go to options and matrix calculations, option 3, and then option again. Go down, determinant of matrix A, so option 3, and that should give you the answer. So this is a fraction, we want it to be in a decimal, so 72.96. So this is simply equal to 72.96 Newton meter. Of course, because of the nature of the unit vector, you can also compute this by hand. This is simply equal to 1, 0.3 times 318.2 minus 225 times 0.1. We can also do it this way if you want to. Notice that the value of minus 0.15 does not come into the calculation at all. So this explains why is it that even though I entered the wrong number in the calculator, the final answer is still correct. Now, what is the significance of a positive moment? This means that the movement points in the positive x direction. Okay, if you happen to get a negative moment here, negative value here, then this means that the movement points in the negative x direction. The next question is a follow-up of the previous question. The friction at slip A can provide a maximum resisting moment of 125 Newton meter about the x-axis. Determine the largest magnitude of force F that can be applied to the bracket so that the bracket will not turn. In this question, the force F is unknown and we are supposed to determine the magnitude of this force F so that the bracket will not turn. Taking into account the fact that the resisting moment of 125 Newton is applied about the positive x-axis. So in this case, we still take the R vector as RAB. And our force vector, however, there's a slight change. So since F is not known, so we simply leave it here. Minus 0.5 Fi plus 0.5 Fj plus 0.707 Fk. The formula to compute the moment about the x-axis is still m sub x equal to I dot RAB cross F, which is given by 1, 0, 0, minus 0.15, 0.3, 0.1, that's taken from the RAB vector, and then here in the last row, minus 0.5 F, 0.5f, 0.707f. Now, if you look at the last row, there's a common factor of f, so we can take it out. And then we are left with just this determinant here, minus 0.5, 0.5, 0.707. And then you can continue to either use a calculator or do some hand calculations to compute this determinant. You will end up with 0.1621f. For the last part, this applied moment has to be less than or equal to 125 Newton meter so that the bracket will not turn. So writing it down, mx equals 0.1621f has to be less than or equal to 125 so that the bracket will not turn. So this implies that the largest f value that can be applied is simply found by solving this equation equal to 125 so that f is equal to 771 newtons. Our next question, determine the magnitude of the moment of the force F given this vector notation about member CA of the tripod. So shown on the left is a three-dimensional tripod where we are supposed to determine the moment of the force F about the axis CA. It is important to note the direction pointing from C to A and not from A to C, and this will have an impact on the final answer. So our first step is to compute the unit vector in the direction of CA, UCA cap equals to, in this case, if you look carefully at the vector CA, it is pointing in the negative x direction by 2 units. So it's minus 2i, and it is also going in the positive y direction by 2 units, so plus 2j, and then to be divided by the magnitude, which is just 2 squared plus 2 squared, and this will give you 1 over 2 square root 2 minus 2i plus 2j, which is just minus 1 over square root 2i plus 1 over square root 2j. Our next task is to determine the r vector that points from any point on CA to any point on the line of action of the force F. And the most convenient one perhaps is just the vector pointing from C to D. So we call this RCD. So here we compute the RCD vector. If you look at the RCD vector, it is moving in the positive x direction by 0.5 units. Now look carefully, the projection of this point D here on the xy plane is actually this point here. And originally the x coordinate is at the distance of 1.5 meters from this line here. Alright, but it ends up at a distance of 1 meter from the same line, which means that it has moved in the positive x direction by 0.5 units. So we say that is 0.5i. In the y direction, now compare the original y coordinate, which is at this point here, and the new y coordinate at this point here. So it has moved a distance of 2 meters. So plus 2j. And finally, in the z direction is very obvious. From C to D, it has moved up by 4 units, plus 4. The next step is to simply compute the moment about CA, which is given by the unit vector CA cap dot RCD cross F. Alright, and this is simply equal to, if we were to substitute our previous unit vector, minus 1 over square root 2, 1 over square root 2, 0, 0.5, 2, 4, and then for the F vector is given the question 50 minus 20 minus 80, and here you can use a calculator to compute the answer. We go to menu and then we move on to matrix option 4. Define our matrix A 3 3. So the first one is minus 1 over square root 2, and then the next one is 1 over square root 2, 0, 0.5, 2, 4, 50 minus 20 minus 80, and then go to option, matrix calculations, go down, to options again, then determinant, and then we choose our vector A, which is option 3, and that should give you the answer of 226 Newton meter. So this is equal to 226 Newton meter. Now, as mentioned, the R vector can point from any point on the axis of rotation to any point on the line of action of the applied force, which means that the vector RAD, shown here in green, is also eligible as an R vector. So we are going to compute the same moment about axis CA using this time the RAD vector. First, we compute the RAD vector. It's simply equal to, in the x direction, it is moving from this point here to this point here, which means that there is a distance of 2.5 meters in the positive x direction, so it's plus 2.5 I. In the j direction or y direction, it doesn't move at all because they all lie, both this point and this point lie on the same line perpendicular to the y-axis. In the z direction, it moves up by 4 units, so plus 4k. So in fact, this vector RAD is even simpler than the original vector RCD. So now let's compute the moment. MCA is equal to U CA cap dot RAD, this time cross F, is equal to, all the rows remain unchanged except the second row. So this is still minus 1 over square root 2, 1 over square root 2, 0. The second row would be 2.504, 504, and then the third row is the same, 50 minus 20 minus 80. This will still give you 226 Newton meter. Please check your calculator. Now, what if instead of taking moments about CA as originally asked in the question, we now take moments about AC. So, what if we have to take moment about AC? What is the final answer? Can we deduce it from the original answer of 226 Newton meter? The answer is yes. In fact, MAC is simply equal to minus 226 Newton meters. Why is that the case? Because if you look at the original unit vector in the direction of CA, it's given by this vector here. So UAC cap would be given by this vector reverse in direction, which means you have to add a negative sign to this. And when you add a negative sign to this, it will eventually be translated to the determinant in terms of a negative sign in the top row, which you can then take out of the determinant, which means that your final answer of 226 will be multiplied by a negative sign, resulting in negative 226 Newton meters. As an extension, we now deal with a follow-up question. Determine the magnitude of the moment of the force F about member BC of the tripod. So instead of computing the moment about member CA, we now deal with the member BC, which is shown by this the dashed line here. So the first step, once again, is to compute the unit vector in the direction of BC. Look carefully at this vector BC. It is moving in the negative x direction by 1.5 meters, so minus 1.5 I. It is also moving the negative y direction by minus 2.5 meters, because this is the projection of the point D on the xy plane. Originally is at this point here, and then finally it is at this point here. So in the y direction, it has moved backwards by 2.5 meters, so minus 2.5 j, and then divided by the magnitude, which is simply 1.5 squared plus 2.5 squared. This will give us something like minus 0.5145 I minus 0.8575 j. Now, the R vector is the vector pointing from, as mentioned, any point on the axis of rotation, shown by the red dashed line here, to any point on the line of action of the applied force. So we still take our R vector as RCD, which was computed previously to be 0.5 I plus 2j plus 4k. So our moment about BC will be equal to UBC cap. This is the unit vector pointing in the positive BC direction, dot RCD cross F, and we end up with this determinant here, 0.5145 minus 0.8575 and 0. The middle row would be our RCD vector, 0.524. Finally, our F vector given the question, 50 minus 20 minus 80. So using our calculator, we edit our previous matrix. Remember that we have a matrix A stored here. So edit matrix A. This was the previous matrix that we compute. Now we have to modify first row. The first element is minus 0.5145 followed by minus 0.8575. The second row remains unchanged, the third row remains unchanged. So that is our new matrix. And then we move on to compute the determinant, option 2 of our matrix A. And that gives us minus 164.64, which is about minus 165. So this is equal to minus 165 Newton meter. So what does the negative sign here actually mean? It simply means that the movement is about a direction opposite to the original assumed direction of BC. Alright, the movement is pointing in direction CB instead of BC. That is what the negative sign here means. Okay, we have finished our lesson for today. We have talked about movement of a force about an axis, and there are certain important points to take note of when you compute a movement about an axis. This vector here is a unit vector in the direction about which we are computing the movement. So for example, in this question, they want you to compute a movement about BC. If you get a negative answer, this simply means that the movement is actually pointing in the direction from C to B instead of from B to C as originally assumed. And our R vector is any vector that points from the axis of rotation to any point on the line of action of the applied force. So there are many choices that you can make. Of course, you will pick the more convenient choices. And finally, when computing the determinant, it may be a good idea to use a calculator to compute, because the determinant can then be recycled for subsequent parts of the question as shown by our previous example. Right, thank you for your time and see you.